Okay, good afternoon. Thank you so much to Francis and Tom for inviting me. I am biologist and I will keep being biologist. I worked basically as a molecular biologist first, and then I switched through time into theoretical biology. Well, I think so that the presentation is download. So the real title of my presentation should include autopoiesis as well, because it somehow goes in that direction. I take Gaia and as I could take as well a prokaryotic cell or a eukaryotic cell like an immune system, or I can take a sequoia, a tree. It's just a case of example that I am taking to learn something, not especially something about the planet system itself, but of living systems. So I think so that check up to the planet, to our planet system can teach us fundamental questions of biology, exobiology, understand causality from inside, since we are living inside the system, about terraforming and habitability, origin of light, and final causation. This is important because nowadays you have this a lot of simulations that you see in color here are like the many models of the climate future that we have.
Alles klar, bis gleich. Tschüss.
And then this is the medium, and this the square dots blue and the dot green are just measurements. So you can see that in time, they are kind of, I mean, the models that we have cannot commute with our observations. Even more, these observations that we have just represent a very tiny time scale compared to the whole evolution of the planet. So this is 4 billions, our planet has 4 billions of years ago. These simulations represent just a spot, a tiny spot on the present time on the using. So, and you can see that our planet also kind of maintain kind of temperature in Celsius between 0 and 50 through his whole story. And over that, based on these simulations that does not commute necessarily with observations, scientists are planning to do geoengineering that will affect everyone. So they are planning to put aerosols into the atmosphere and started to manage in somehow the system, and that they call the stewardship of the air system. So the idea is basically that...
Excuse me, it seems that you do not share the screen.
Sorry.
There's the yellow frame. On the side, there's the zoom button, which is
okay.
And then you see.
Ich bringe die dann auch gleich mal den Tee. Kannst du...
Okay. So the basic idea is that recent time, the planet have this attractor basin from glacial, so it was very cold. We enter into interglacial time and do some anthropogenic impact. We can enter into what is called the hothouse Earth. So this is a picture kind of resemble a little bit the Waddington epigenetic landscape. And the idea is that humanity can in somehow do geoengineering to, or can do climate policy making. So we can implement a lot of measures like the COVID measures that we are doing now, kind of similar perhaps, to avoid we consume too much CO2, and then to put again a planet into a stable interglacial zone, so don't get to go into a hothouse phenotype of the planet. Margulis regard this like stewardship of the Earth seems repulsively anthropocenic to me, even though such intentions are laudable. Why she think like that? Because these simulations and these ideas are based on the thing that we see the planet as a just life-infested rock, no? Like, which is as an absurd thinking as the body of a cell as an infested, cell-infested skeleton. So we are not just an infested cell skeleton. We are more than an infested cell skeleton.
We are the virus.
And then this question whether the planet just it's a rocky planet was challenged by NASA Viking 1 mission. So with the question whether there is life on Mars. So this Viking mission to Mars was to know whether we can find life out there. And they give this task to James Lovelock that in 19, he makes 100 years. He's still alive. There was a party there in Exeter on his, and then he really so when the NASA put the question if there is life on Mars, he really on Schrödinger book. So he was inspired by that. And he said it's the book that most influenced my own thinking. So he basically, in Schrödinger book, was dealing with a general question: how organisms remain organized in the face of the second law of thermodynamics. And Schrödinger came with two kind of sort of answers that he thinks that we would prepare to find a new type of physical law based on these two answers. So it's negative entropy, which is based on open systems and a code script. So negative entropy, a code script is you can kind of pack what is the code script in Schrödinger terms. It's the architect's plan and builder's craft in one. This is going to be later, is going to be very crucial to the talk. And the negative entropy, which is the marvelous faculty that a living organism feeds upon negative entropy to compensate the entropy increase it produces by living and thus maintaining itself on a stationarily fairly low entropy level. But nowadays, biology and science in general, so this is 2018, 75 years after What is Life, publication. So there is no such drastic solution seems to be needed, biology said. No? Schrödinger gave to his code script too much agency. And this isn't how it works. So you just need to rely on Shannon and cybernetics of Nobel winner. Linus Pauling considered that entropy was a negative contribution to biology, value and superficial. And another Nobel Prize, Max Perutz, says that what was true in the book was not original, and most of what was original was not to be true, even when the book was right. So this is the stage that science and biology is at this moment about regarding to Schrödinger work. In any case, Lovelock assumed the negative entropy as an important concept. And based on the negative entropy, he developed a series of planetary scale observations that led him to formulate some experiments to how to detect life on Mars. And then started also a huge research program called exobiology, or planetary exobiology at least. But the same methodology is still used so nowadays. So it was by reading, Lovelock said, What is Life, that I first realized that planetary life was revealed by the contrast between a dead planet, Mars, and the Earth. So by applying negative entropy, he figured out that the planet, that the Gaia phenomenon, we call the Gaia phenomenon, that does not happen on Mars. What is this Gaia phenomenon? It's kind of a planetary scale life phenomenon. He discovered by watching the spectra of the atmosphere. So here is the Mars atmosphere, and it's very oxidizing atmosphere. So you have a lot of little CO or oxygen, and you have a lot of CO2. And you don't have methane, so at least methane, I will concentrate on methane or non-hydrogen. While the planet, the Earth planet, you have a lot of oxygen, little CO2, and methane, a lot of methane. These two gases are very reactive. All right, these two gases are very, very reactive. So if you put these two gases together, they explode. But the question is that you have concentrations of methane and oxygen on the atmosphere, but you don't find explosions everywhere, even though these gases are very reactive. So the question is, how is possible that we can find this kind of anomaly or far from equilibrium concentration of these two gases on the atmosphere? And then, because at that time, Lovelock was sharing office with Carl Sagan, and Carl Sagan was the husband of Lynn Margulis. So that Carl Sagan said to Lovelock, okay, you can talk maybe with Lynn. And indeed, Lynn Margulis at that moment was researching who were producing methane. So, and at that point, Margulis found that methane was completely biogenic. So 99.99% of the methane on the atmosphere, on the Earth's atmosphere, is produced by methanogens. So they started a fruitful collaboration, and they figured out indeed that the gases that we have on the presence of living systems. So here you have atmosphere, our current atmosphere in an artwork graphic. And this, if the planet will be dead. So you can see that diversity of molecules that life produce at the planetary scale and concentrated and flux on the atmosphere is completely different from a dead planet. And then they formulate the family's Gaia hypothesis, which says that atmospheric homeostasis by and for the biosphere. So this by and for, of course, biologists and scientists didn't like, but because it looks like too much, we carry with too much teleology. So neo-Darwinists react, especially Ford Doolittle and Richard Dawkins, react that this is teleological. So the by and for is kind of, we cannot accept on science, nor in biology. Organisms cannot reach a common good by natural selection. How is possible that we can have atmospheric homeostasis, which is a common good on the planet, while natural selection is acting on competition between species? And that natural selection cannot act at the planetary level, because it's supposed to be that natural selection is act on the subplanetary level. So in response to them, Lovelock and his unique and one student, Watson, they developed this this model that call it Daisy World. So Daisy World is a hypothetical cybernetic planet that first start with black daisies. So you can see here little ones, and this line is the sun luminosity. This is the temperature. This is the temperature, and this is the line A is the sun luminosity, which increase constantly, and the B is the temperature of the planet. So while the temperature started to increase, the planet started to get a little bit hot. So some daisies, white daisies, are started to grow, and by the color of the white, the white is by the albedo, which is the reflectance of the sun, of the light, take away the heat, so they can regulate. So the main take-home message of this of this hypothetical planet was that, you know, you can get a common good, a temperature self-regulation, without appealing to natural selection. So you don't need daisies to compete each other. But that creates a side effect on the Gaia hypothesis in general, which was James Kirchner, you know, he is a geophysicist, and he said that, okay, he really then on the question of whether Gaia hypothesis can be tested. And a quotation of him is that Margulis and Lovelock proposed that a test for Gaia is to consider what happened if life were now deleted from the Earth. And Kirchner thinks this is, of course, a test for life, not a test for Gaia. So Kirchner is confusing a bit, saying that Gaia is a feedback and not life. So this creates, of course, a mess on the hypothesis. And then you have, you know, this is kind of a resume what happened from the formulation of the hypothesis to now, is that you have the Gaia phenomenon, which is this observation that that life can express itself at the planetary level, and you can measure that. You can observe like Lovelock observed by applying negative entropy to Mars. But there is a move from saying that you can recognize life at planetary level to say that the planet itself is alive. So this is the distinction between the Gaia phenomenon and the Gaia hypothesis, and how you approach the Gaia hypothesis. So all these discussions about evolution, about daisy world, about whether it can be tested or not, create the Gaia theory. So the Gaia theory nowadays have at least the taxonomy have three main topics. So it's whether you can approach that by just feedback self-regulation, which then you have the homeostasis, ultra-stability, sequence selection, whether you can go in the direction of Alex Claydon, non-equilibrium thermodynamics, and then you apply some self-organization, optimization, maximum entropy production, or you go straight forward to adaptive evolution, which is planetary, whether the planet is a unit of selection, whether is there what clad competition or progress by accumulation. So you don't appeal anymore to somehow of competition. But the question is whether these theoretical developments can say whether a planet is alive or not. So in other words, the Gaia hypothesis is best presented as the hypothesis that supposes the Earth to be alive as a living organism. So the question is whether these three theories can tell us what is a living organism. So how we can take the Gaia hypothesis at face value. Indeed, the very first critique to the Gaia hypothesis was formulated by Hayes von Foster in a nice paper that he published that it's Gaia cybernetic badly expressed. So in that paper, Hayes von Foster already was saying, guys, Gaia is not necessarily a feedback system. It's more, it could be more similar to an autopoietic system. So based on this paper, Margulis, of course, was, as she's co-author of the hypothesis, was saying, okay, yes, indeed, Gaia could be an autopoietic system because it's self-producing somehow. And then he, in this nice, first published as a paper, then published as a chapter in this book, he said, big trouble in biology because you confront two main kind of theoretical explanations, which is the mechanistic neo-Darwinism or physiological autopoiesis. So therefore, the research program was, okay, we will include then a new kind of biological theory to attempt to explain the Gaia phenomenon and therefore to approach the Gaia hypothesis. And this is based on autopoiesis and MR systems. So an autopoietic system, we can start there, is just a unity, a biological unity that is coupled with its environment. You can abstract that it is a metabolic network that produces relations of molecular products that constitute a boundary, and this boundary specifies the topological dynamics of the metabolic network. When this is coupled with, because it's an open system with environment, you get a biological unit. Maturana strongly emphasized that autopoiesis must always be molecular. What means this? That social autopoiesis, it's not too much common sense to talk about social autopoiesis or another kind of autopoiesis, because autopoiesis takes place at the molecular level. There are autopoietic systems of higher order, like Gaia, integrated by lower order autopoietic units like cells and multicells, that might not be the components realizing them as autopoietic systems. So we, in our domain of realizations, we don't realize Gaia by ourselves. It's our byproducts at the molecular level. So there are higher autopoietic unit systems whose components are molecular entities produced through the autopoiesis of lower autopoietic entities. In other words, Gaia is realized if it is realized as a molecular entity. So the closure that we, for instance, as a multicellular systems, our closure is at the molecular level, not at the cellular level. So our cells does not get operational closure by themselves. It's the product, the molecular products of them that make us, we get in an operational closure. That's why we, as autopoietic entities in the molecular domain, can have we can have in somehow autonomy with respect to, for instance, immune cell. Why immune cell can have autonomy? Because our domains of realization, as they are molecular, while they are coupled with each other, they are in somehow at the level of the behavior, can have some kind of degree of autonomy. So our immune system can have a degree of autonomy because we are realized as a molecular entities. Well, but this is a secondary topic. So the Earth atmosphere is, if you compare what will look like the planet if will be deleted live, you will have this difference regarding the component concentrations of the atmosphere. So there is a huge difference because this surface flux of the components are in logarithmic scale. So you really can have quite different. So indeed, these components are highly kind of connected. They are indeed themselves the aerosols, the clouds, and the greenhouses, and the ozone. So these are the 3 layers of the planet, or the 4 layers that really protect, like, from radiation from outside. So you know that if X-rays enter to the, or UV enter into the surface of the planet, you can mutate things. So indeed, the planet, the whole boundary of the planet is produced by the biotic and abiotic activity. These are just observations. The water, for instance, if you observe the water of the planet, so this is spot in relation to the radio of deuterium and hydrogen, and you compare the water of the other asteroids and planets on our solar system, you can find that there is statistically, there is a very low statistic probability that the water from outside came to the planet. So it's most likely that the water is self-produced, that the oceans that we have on the planet indeed are metabolically self-produced. At least this is the observations that suggest this kind of measurements. And this water, of course, has, and the biotic activity in itself has a huge impact on the geochemistry of the planet. and interacts with the interior of the planet, which interacts with the exterior. So autopoiesis is at least a plausible scenario for the instantiation of life organization on the planetary scale. How we say that? That you can have a geo-hydrometabolic network that produce an atmosphere, and the atmosphere allows indeed to the topological dynamics. So we cannot, you know, living systems in general cannot exist without our bond, without our atmosphere. Even though if you take a very like resistant extremophile bacteria like radiodurans, for instance, outside the planet, it is not viable for more than 1 week. So necessarily needs the habitable conditions of the planet. So based on this kind of rationale and how the components vary on the geological time scale of the planet, with Thomas and Pedro, we kind of construct a list of reactions that came from abiotic and abiotic. So we mix up biotic and abiotic reactions that are real reactions that happen on the planet, based a bit on the evolution, how the evolution of microbes took place through the geological history. And we found that these chemical reactions can indeed self-maintain and form these organizations in terms of chemical organization theory that resemble indeed the story of the planet itself. So you can find these organizations that looks like they were the primitive Earth, the Archean Earth, and then how, depending of what they are, so you can find kind of similarities of how was the evolution of the planet itself. So we published this paper like beyond the planetary scale feedback regulation, in the sense that self-productions must came before than regulation. So if you wanted to produce something, if you imagine a fabric that it is producing a box, first of all, you have to think on the production, how you are fabricate the box, to later on think about the regulation. So regulation is somehow come later than production. But autopoiesis, you know, puts you another level of explanation as well, which is cognition. Living systems are cognitive systems, and living as a process is a process of cognition. So the question is whether code can tell us something about cognition. This is based on the thing that you have these autopoiesis and explanatory domains. So you have the self-producing domain and how the autopoietic unity interrelates with the environment, which is the relational domain. And this relational domain is like how the system acts on the environment and sense upon the environment to have these sensory effector coordinations. And this can best be interpreted as the openness of the system, and therefore as a fit upon negative entropy. Indeed, you can interpret this relational domain of autopoiesis as the negative entropy that Schrödinger was talking about. Because Schrödinger said, if I had been gathering for them physicists alone, I should have led the discussion tune on free energy instead. It is more familiar notion in this context, but this is highly technical term, seeming linguistically too near to energy. So Schrödinger is saying, as for making the average reader alive to contrast between the two things. So Schrödinger, what it is saying, Schrödinger, is that free energy or negative entropy is not Gibbs free energy. So it's not just thermodynamic energy. It must necessarily include in somehow acting and sensing. More explicitly, you can find in Schrödinger, like by which the individual responds to alternate situations by accordingly alternating behavior. A property of nervous processes is a property of organic process in general. So it's not, again, focusing on living systems, like only living systems that have a nervous or a brain as a cognitive systems, but in general. So this is best interpreted, I do think, from my opinion, that this Schrödinger free energy or negative entropy as free energy minimization. But this is a move, of course, it's my move, I would say. Because you can interpret this, I mean, at least Carl Princeton interpreted like this acting and sensing as a Markov blanket, which is you have the internal states of the system and the external states of the system. And these are related, interact through a Markov blanket, which is conformed by active and sensory states. So in somehow, minimization of free energy is formalizing the relational domain of autopoietic systems as if they perform inferences. How? So because the question of acting, so it started as a theory of the brain, but it can generalize to all living systems. So the brain or a living system acts on its environment to perturb the environment and to gather information about this perturbation of the environment, and therefore generate a generative model to predict later on how the environment will fluctuate. So the idea is, if the snowflake will be a living system, it necessarily will need to act in the phase boundary transition to remain alive. So otherwise, you know, just drop and the snowflake become a drop. But the take-home message of the free energy principle or the free energy minimization is saying that the snowflake, if it will be alive, it will need necessarily infer this phase transition and act upon. So here is like with swings, no? Also is kind of this free energy minimization it's similar to active inference or prediction error. So you can see here, you know, if you observe this, you see a wolf, but at the end point, the wolf is just the shadow of a cat. So a thought experiment could be if you put a glove in your hands and you have coins of €2 and €1 with the glove, you can predict what is €1, what is €2. So probably you will need more time to kind of figure it out in your pocket what is €1 or what is €2, because your blanket state in terms of sensory state will be interfered. So if you interfere your blanket state with your sensory state with a glove, it will be much more difficult to you gather the information and therefore infer what is €2 or €1. No? The basic idea is that. So indeed, in Maturana, you can find this quotation that a living system, due to its circular organization, is an inductive system and functions always in a predictive manner. So what about Gaia? Does Gaia predict at all something? This was put it forward by Carl Sagan, indeed, which is called the Weeks-Young Sun paradox. So the evolution of the stars, all stars and our sun as well, started with a very little star that is very weak. It's very weak, so does not have much more energy. And so this is the time of the planet, 4 billion years ago. And if you will let just the Earth be a responsive system, a reactive system according to the evolution of the sun, the planet will be frozen until at least 1.4 billion years ago. So the planet will be completely iced, so frozen completely, if will not act on the environment. So this is, the thing is whether you can have a sun, a very weak sun, and there is geological evidence that at 4 billion years ago, we had liquid water on the planet. So we had plenty of geological evidence that the planet 4 billion years ago, we had liquid water. So the planet has liquid water. How is possible that if the sun was too weak to allow liquid water, that the planet had liquid water? That's why it's a paradox. And I think so that the paradox was somehow can be resolved by the issue that to implement, at least to frame the planet, the autopoietics, as autopoietic systems in terms of Markov blankets. So you have an internal state, which can be the biosphere. And this biosphere is producing first a lot of greenhouses. So this is something that already Lee Margulis was saying. So we produce a lot of methane, and this methane allows the planet be warm because the methane doesn't allow the energy of the sun go back to the space. So it allows to stay. And at the same time, this is allowing the liquid water on the planet. So you indeed can frame the paradox, the sun paradox of Carl Sagan in terms of free energy minimization by equipping the planet with a Markov blanket. That what the planet is attempting to do. So this is an implementation of this idea of this perspective paper. So we put basically the temperature of the temperature at the Earth surface. So the temperature at the Earth surface that arrive from the sun, the biomass in terms of internal states, the CO2 as a greenhouse gases, and the answer response. So I'm gonna go quickly here. Basically you have a low response in terms of CO2 and a dynamic of the biosphere much more active than the active state. The basic point is that you can have a sensory, a blanket state that it is synchronizing with how the sun is how the sun fluctuates. So the sun can fluctuate, and the sensory state of the planet can track this fluctuation. Indeed, if you perturb the temperature, the external temperature of the planet, you can have immediately answer in terms of Markov blanket of the planet. So here you can see more clearly. So the blue line is the inferred solar radiation, how the biosphere is inferring how the sun fluctuates. And the red is the actual solar radiation. So you can see that, through time, the biosphere is indeed able to track how the sun fluctuates. This is, of course, not saying that the planet itself is thinking as a whole, but in somehow is pushing us again to the Gaia hypothesis in itself, that there is a by and for the biosphere. So we can come back without any mysticism or saying that it is not scientific issue. Come back that the planet itself and the biosphere itself is acting on its own persistence beyond the anthroposphere. The second, so this was about autopoiesis, and about the MR system. Of course, it's much more controversial can be, but I will go quickly. So the code script is the other side of the new physics of Schrödinger. The first was negative entropy of free energy, and then this is the code script. So the code script was the architect's plan and the builder's craft in one. But molecular biology, and started with Sidney Brenner and Francis Crick and all these molecular biologists, thought that this is not the case as I showed before, that the architect's plan was not necessarily be together with the builder's craft. What is that? That the architect's plan is the genome. So you have the genome, so you have the teleonomy, this idea of biology is about teleonomy. The architect's plan is the genome. And the builder craft is the von Neumann self-reproducing automata. So they make this interpretation of the code script of Schrödinger in a completely different way that Schrödinger was enunciating. The more radical side of Schrodinger, as the code script is concerned with tuning inertia, which is linked to material chaos into gravitation efficient, because we are talking about mean physics here. So I think into a force, a molecular into a Mendeleev factor, then an extension of mean physics. So you can have here a complicated network of a cell that can be mapped in a simple diagram. So you can have all components that are transformed into other components that are transformed by a catalyst, so by F. So you can indeed reduce this kind of complicated diagram into this one. So someone will say this is a complex thing, but it is not. It is just a complicated in the head of relational biology, or at least of Robert Rosen. So because this map is just a part of a whole thing that when you say who produces F in this thing, you necessarily must really in something inside the system. So who produces F was produced by using some kind of B that another function phi was using to produce F. Then if you ask why exists phi, you need another component, which is a subset, inverse map of B produce phi. So in other words, Rosen is suggesting, I did not quote him directly, but he's suggesting that the code script is the MR system. So that indeed you can find the architect's plan and the builder craft in one when you are watching at the MR system. And his main theorem summarized that then a material system is an organism if and only if it's a closed to efficient causation. Well, the theory kind of predicts what it predicts, that to get a folded enzyme, necessarily you need a living system. You cannot because a folded enzyme is an efficient cause for Rosen, and this necessarily needs a living system. You cannot design and produce in the lab a folded enzyme, at least that acts catalytically as is acting inside the cell. And indeed, there is a lot of attempts from powerful, very powerful algorithms from Google and so on, that they call deep mind AI, that, you know, these structural biologists that really on computational models, but they don't know the theorem of Rosen, they think that they will at some point predict the folded enzyme based on just on the information of the DNA sequence. And this AlphaFold 2, for instance, you know, it's kind of the most advanced algorithm to predict the structural or the shape of the folded enzyme based just on the physicochemical landscape and on the sequence of the DNA information. But on the other side, you know, if you give a kind of self-referential system to a machine learning, this can lead us to undecibel problems, so undecibel problems. Still, you know, I think so that the theory of Rosen is telling you something deeper about whether things, biological things, can in somehow be implemented in algorithmic terms or not. So the most important, I think, so for the talk as the other side of the negative entropy is that Rosen thinks or thought that the possibility of separating finality and final cause from teleology, retaining the former while discarding the later, and the incorporation of final cause in the organism in the form of the additional modes of entailment it requires, it is not only possible in formal grounds, it is crucial. If you see this mapping and we ask why exists B, so you have two answers. B exists because A, which is the material cause, this continuous arrow, and because F, because F is acting on B to produce F. So the efficient cost will be F. This is dotted, the dotted arrow. Then if you ask why F, you will say the final cost of F is to produce B. Or you can ask why A, and the final cost of A is to produce B. So indeed, you can formally approach final cost in somehow by going to this. But the thing is that this mapping, you know, the F and A are not entailed in the system itself. So I as an observer are addressing the final cost to the system. While in the MR system, the finality itself is inherently to the MR system. So indeed, what Rosen was suggesting is that this new physics is indeed not only the incorporation of the final cost in the organization of living systems, but how they interrelate each other, how material, efficient, formal, and final causes are entailed each other, are interdependent of each other. So you can have here, for instance, and most importantly, this final cause is assumed to be in the form of anticipation. Anticipation is something different from feedback loops. So you have here a feedback loop. No, you have a pathway of a metabolic pathway, enzyme that is producing something. And when this when this go high, you know, there is a feedback on the enzyme, so the enzyme can stop. But a feed forward is like when you increase the component A, this component A can feed forward in future events to stop the action of the enzyme. In other words, so an anticipatory system is a system that contains a predictive model of itself and of its environment, which allows it to modify the present behavior of the system on the basis of anticipated future effects. So what means this? So there are plenty of evidence that this is taking place on microorganisms, on plants, on a lot of sorts of living systems. So the basic is that a feedback is this. So you have a system that cross an error. So it's an error contracted, modify some kind of threshold, and by a feedback loop, come back to the normal stage, so to the range of states. While in anticipation, what anticipation is telling you is that the system has its model of this future possible modification and of the error, which is in red here. And based on this model of the future, can act in order to don't change. So it's kind of qualitatively different from a reactive feedback system. We attempt to, in somehow, to ask whether the planet is a MR system. This is an open question. I will not give a final answer, but in somehow it's telling you that life on the planet and the planet itself are in somehow self-referential each other, because the planet cannot exist without living systems, but living systems cannot exist without the planet. So this puts a lot of constraints whether we can make Mars, for instance, terraform Mars, or whether we can give life to another planet, because how you will put living systems in a dead planet to produce an atmosphere if already the theory is telling you that the both are necessarily linked. So a way to address this at the planetary scale is to watch in somehow some evidence that, for instance, the Amazon as a forest is able to make its own rain, and it's able to have to sense in somehow when the sun, the season, the drought season is gonna come, and anticipate the drought season and to start to produce more clothes. And these more clothes give, of course, continue operating the system. And by producing more clothes, it's also pushing wind, the Amazon. And by pushing wind, it's pushing also the nutrients from the Sahara. So indeed, this is not anecdotal. This is something that on the planet, it's not taking place just by chance. It is things that are acting on somehow on anticipative basis to keep persisting. It's an open question, whether the planet is an anticipative system, but at least we have something to bite in terms of free energy. So some conclusion is that the Earth system is just one example, more to learn about biology, thus new physics in somehow. The Earth as a self-producing autopoietic unity might act beyond feedback mechanisms. Possible autonomy at the planet scale might be difficult to deal with present-day climate models. So climate models cannot still incorporate autonomy and feed-forward loops on their models. Free energy minimization might offer one of many ways to model anticipation and autonomous at the planetary level. And connect COT, chemical organization theory, with active inference will be highly relevant. I will leave with a quotation of Heinz von Foster that says, change arises from the organism's inability to make infallible inductions, while necessity from the ability to make infallible deductions. And thank you so much.
Thank you, Sergio, for your insightful talk, full of insights. Very nice. We have some 10 minutes for questions before the next talk. Anybody? Okay.
But I always thought so. Maybe.
Yeah,
No
no,
worry.
it's
I have a question about the difference or relationship that you make between, say, autopoiesis, generally self-maintenance, and anticipation. You seem to treat the two things as not synonymous, but if you have autopoiesis, then you have anticipation. But that's being discussed, and it seems not too obvious. Not because something is circular, but there is anticipation. One of the most quoted paper by Ezekiel Di Paolo makes precisely the difference. You can have an autopoietic system that keep doing something, but is unable to react to perturbation. And then you have a system which is an adaptive system, which is able to modify behavior, either because it has different possible behavior, or because it just invented a system way of doing, which is able to counter perturbation until it's something. So if that there are two different levels of complexity there, and I think that when Maturana is saying, well, a living system, a cognitive system, it's not that clear that an autopoietic system, a simple autopoietic system, is complex enough to be anticipatory and cognitive. But there's debate about that. So are you making this?
I mean, I think so that, autopoiesis has this approach that it is in terms of CO2, but also there are works that I did not show of Letelier and so on, that they kind of say that, okay, autopoiesis is best represented or best modeled as a MR system. If you take the side of the MR system, the MR system by itself, the system needs in somehow to know what A is gonna take from outside, because A is A1, A2, AN, in order to produce a specific B, to produce a specific F. So the system in itself, in its self-fabrication processes, contain already anticipatory models.
Oh, okay, I disagree with that. I think that is not complex enough. But this is, I think that the point that anticipation is the capacity to, you have to Francis would agree with that. If you know if the system is a physical system, you have to perturbate the system. It's not because you have a cycle like that, which is already very complex, of course. Then you have this idea of adaptivity.
Right. You can see here, this red line is a perturbation. So, you know, the system goes here and you perturb the system and the system change, then adapt and come back again to normal. So this is kind of the reactive system. So no, in order to the system, you know, change needs to pass through the perturbation and then error, and then they compensate the perturbation. So this is purely reactive system because the system needs to cross the error, needs to make the mistake in order to, say, okay, I did a mistake, you know, that can make me die. And then I have to, by feedbacks, it's assumed, come back to this non-entropic trajectory, to the living trajectory. While the anticipation is telling you, and not only anticipation, the free energy, the active inference, Carl Princeton explanation is telling you the system is not crossing the mistake, it's already having a model of these potential errors in the future while not violating causality. Just having some models of these possible fluctuations in order to act on the present to avoid to change. So there is no error counteracting, it's error avoiding. Error avoiding.
My point is that capacity is not reducible from autopoiesis itself. You need a bit more than that. Even for a system, I doubt that you get that simply from the standard model. It's a bit more. So
sure.
This is something more than just circularity.
Yes, yes. Yeah, no, I do think that if you stick strictly into Maturana and Varela, definitely, I agree with you. Definitely, I agree with you that they don't contemplate these things on. Perhaps Varela in the later periods wrote some kind of essays on intentionality in biology and the paper with Weber, no, Life After Kant. Perhaps there he elaborates a bit more. But it is true that in the 80s they didn't. But I think so that was kind of a way to don't be catalogued as a vitalists. I think so that they were kind of afraid to don't be.
I think that should be testable. So you take the model of Maturana, Varela, Uribe, and you just show in that model by simulation, let's say that there's anticipation going on. Maybe using information theory should be possible. But just I wanted to say something on this slide.
On the
yeah. Because I think this slide,
on this,
I think you have to add something. Because if the red is a real perturbation like in control theory, you cannot predict it because that's a definition of perturbation.
It's a reactive system.
Yes. So, but of course, there's a concept of Störgrößenaufschaltung in German. It's called that you indeed anticipate how the system will change by some observation, and you build a controller that anticipates how the system will change. But for that, to do the anticipation, you need another little red bar at the beginning somewhere.
Yes,
so in order to predict that tomorrow there will be light in 24 hours, you need a little bit of information that there was today light and so on. So I think to make the thing fair, you have to put a little bit of red stuff at the beginning.
I agree with, yes, I agree with you, completely agree, which was the discussion that we will having with Francis, whether we need a feedback first in order to build up generative or predictive models. But you can have hypotheses of the future without necessarily crossing to perturbations. So for instance, take the example of climate models nowadays. We did not run away in terms of climate change. So we are still, you know, enjoying kind of, let's say, the habitability that we are living on. But based on the inferences that we did not cross yet as an anthroposphere, we are attempting to make policy making now for the future, even though we did not pass that future yet. You know, either the future is catastrophic or not. We are at this moment, we did not cross that perturbation yet in order to make the predictions.
We take information from today. So we know that we are at, let's say, 3 billion time point. Yeah, that's an information we take. We are not at 1 billion time point, we are at 3 billion time point. So we take some information of today to make this prediction. So it's not that we have.
No, I think it's encoded in the cloud, like in the cloud thinking. That's kind of like encoding the perception of making this, so it should be encoded there.
So you can, in dynamical terms, you can say like the state of the system depends on the past, on the present, and on the future. But this future, of course, is not violating causality. So it's a hypothetical future that not necessarily I agree with you that we need to gather information because as a living systems, we sense upon and act upon the environment. So the question is that you can allow it to make hypotheses without necessarily being perturbed. You know, and that is I think so that the difference between a pure reactive system, error counteractive system, with a necessarily anticipative system. And the great things I think so of the MR system is that this is embodied in the self-production. So the MR system is able, incredible, to embody this already in its self-production, which is, of course, something that in autopoiesis you cannot see that. But in the MR system, you know, you consider the set A not as a one element, you consider as an infinite elements of the environment. And you consider the catalyst here as F also not as a one catalyst, you know, as different catalysts that are specific to a specific A that are produced by a specific B. And to the system produce this specific F apart from a specific B necessarily needs information.
I don't understand that.
Yeah, but we need to move it.
Okay, we can discuss later.
Because Michael Levine has some time, and we move now to the. Thank you again. And it's the normal, you know, like no surprises that we are excited. I also have some of my questions. And now it is my pleasure to introduce our first not in presence speaker. We are without wanting or knowing, we are starting a new way to do conferences, which is not entirely virtual, not entirely online, but meeting groups and distributing it somehow. So interesting form of, I don't know how to say, superposition between in presence and on virtual conference. So Michael Levine is going to be our next speaker. You are now in exactly. Michael, do you hear us?
What? Yes, yeah. I hear you perfectly.
Okay. So I was wondering, where are you at now?
I'm at the Tufts University in Boston.
In Boston. Boston. Okay. Yeah. So I will stop sharing slides so you can take the screen now.
The host has disabled screen sharing.
Okay, I will enable. I will stop recording.